Okay, we're going to put together the whole hypothesis test for this particular situation now. Regular times Roman takes everyone in the world on average 22 seconds to read this text. We give it some fancy GG text, and we want to see if the mean we get here is really far away from 22. If it's really far away from 22, in fact, if the true mean was 22, it would be almost impossible to get a mean, to get a sample like this. Then we can reject 22. Alright, so let's go through the steps here. This is a structure that we're going to use right off the bat. Now, it's in here that I want you to put your units of measurement. Okay, I should be able to read this and know exactly what this problem's about. So take your time, write it all out in this particular step. Something like the true mean reading time of these 4 paragraphs using GG text in seconds. Okay, so make sure your units of measurement are in your population parameter. Alright, the null hypothesis, we're going to assume that there's no difference with time Roman. So you could put equal to 22. Quite often you'll see 22 seconds here. You said it here, you don't have to say it here again if you don't want, but make sure the units of measurement are here. So, use equal to 22 seconds, and the alternate, we're trying to prove that it's more than 22 seconds, so greater than 22 seconds. Alright, here is our significance level. Let's remember what this means now. Let's say in this problem we set it to 5%. That means this. You go out and you get your sample mean. If the real mean is 22 seconds, that means all of these X bars are going to be around 22 seconds, some higher, some lower. If I get an X bar that's a lot higher than 22%, but there was still about a 4% of these were like that, I'm going to still say I reject 22. Even though there was about a 4 or 5% chance of getting an X bar like that, I'm going to say, gosh, that was so remote, I'm still going to reject 22. So that's what we're setting at that 5% alpha. If you go to a 1% alpha, okay, you're saying something else. You're saying, well, I'm only going to take the most extreme of these and say 22 is wrong. Okay, so that's what this alpha level is. It's very important as to the threshold of the amount of evidence that you need. So we're going to set it at 5% in this particular problem. Our assumptions, some interesting things here. Simple random sample, I told you it was stated in the problem. We're good there. Can I use this formula? Yeah, 25 is less than 10% of all the people that could read these 4 paragraphs. Sure, that's infinite. All right, do we have a normal sampling distribution? Okay, I didn't say anything about the population distribution. That one doesn't work. Our sample size, although, 25 is getting there, but it still didn't beat 40 or more, so central limit theorem doesn't kick in here. So we've got to go to that third assumption in big bold letters because you have a small sample size. You have to assume the population distribution is normal. Make sure population distribution is there. Alright, now we're going to analyze this sample, and you kind of saw some different things. Those of you who did a box plot, did you see an outlier? Okay, so I honestly, your analysis of the sample, you could go either way with it, and I would mark it correct. If you said an outlier is noticed, so that it causes some concern about the assumption that the population distribution is normal, I would have taken that. But take a close look at it. Say you didn't do it and you drew the line out to the dot. What would you say about the symmetry of that box plot? Pretty symmetrical, isn't it? So if you said something like, although there is a presence of an outlier, the data from the sample is fairly symmetrical, that helps with the assumption that the population distribution is normal. Go either way with that, I'd give you full credit. But analyze the sample and know what you're looking for and what it tells you. Okay, this is the test statistic we're going to use to find out how far away our sample mean is from the what they say is true. All right, here, now in this area you've got to draw your picture. Okay, we're going to assume all these X bars are centered at 22. We got, what was it, like 27 point something? 27.08. Now I look at that, and I'm like, wow, that's far away. Okay, they're saying the real mean's 22. I got a real mean of 27. That's pretty far away from 22. But now we analyze how many of those x bars would be 27 or more. Okay, it's 5 away, but would that be common if the real mean was 22? Okay, now we go calculate this, and this is called the p-value, probability of getting a sample that extreme if 22 is real. All right, we plug in our numbers, so you've got 27.08 minus 22 divided by 6 square root of, what was it, 25? Did you get 4 point something? 4.24. 4.24? Don't forget to go put your z-scores, the standard normal curve, under your picture. This is pretty much off our chart, so this is approximately what? 0. Now know what that means. Look, if 22 is the real mean, there is no way you can get 25 people together and have them read this and get an average of 27 seconds. 22 cannot be right. Okay, I've tweaked these last 3 sentences again. You know, it's been 15 years. I think I'm just starting to get this right now. So it's a little bit different than what you wrote yesterday, so let's go through it. See if this makes sense to you. Obviously, we're not doing length of name anymore, but assuming that the true average time, the mean time it takes to read GG text is 22 seconds, there is, and in this problem, no chance of getting a sample mean of 27.8 seconds or more. Now, since our p-value is less than the alpha level, and then I want you to put that math in here. So in this problem, our p-value was 0. That is less than 5%. If you want to put them in percents, you can put 0% is less than 5%. So you're giving the person what those actual values were. We will reject 22 seconds. So what have we got is the last sentence. Therefore, we do have statistically significant evidence to say the true mean reading time is greater than 22 seconds. We have proven that beyond any reasonable doubt. In fact, the p-value of 0, we have proven it beyond all doubt.
Are we rejecting 22 as the time to be Roman, or are we rejecting?
No, in this case, you know, we're kind of using that as a little bit different here. It's not the same thing. We're rejecting 22 as the true mean of GG.
Okay.
Yeah, we're not refuting the 22 claim of times Roman. We're so this is all assuming, you know, assuming that 22 seconds for GG. Okay. Do a few of these tonight, the whole thing. This is the process that we can go about proving someone wrong. Okay, what happens if we have a two-sided test? Now understand what that means. It'd be like someone says that the GG time is 22 seconds. You're like, I'm not sure if it helps you read it or hurts you read it. I just know 22 is wrong. And I want to prove 22 wrong. It could be more than 22, it could be less than 22. I don't know which it is. I just know 22 is wrong. So in that situation, our alternate hypothesis is that it's not equal to 22. Now let's think about this now. If I now get an x-bar, a sample mean that's way more than 22, I'm going to reject 22. But also, if I get a sample mean that's way less than 22, I'm still going to reject 22. So I have two areas where I'm going to reject. The most extreme on either side I am now going to reject. So this now becomes your picture. So in this particular problem, our mean was 22. That's the x-bar we got. But what we want to know is what's the probability of getting an x-bar that far away in either direction. Because in either direction, we will be rejecting the null hypothesis. So what I need you to do, this had a difference of about 5. Subtract 5, so that tells you the x-bar over here. The p-value then is this plus this. Now, it's symmetrical. If you want to take that value and multiply it by 2, it's the same thing. But this is now the picture. These are the X bars, the chances of getting an X bar that far away from the mean in either direction. Because we're going to reject if it's in either direction. If I get an X bar either direction, I'm going to reject the null hypothesis. So in this problem, since it was 0 here, 0 times 2 is still 0. Okay, but if this would have been 2%, then 2%, 2%, so our p-value would have been 4%, and that's what we compare against the alpha level. Okay, so when you get a two-sided, that's what I want your picture to look like, and that's how you calculate the p-value. Okay, all right. So when you think about it, there's actually 3 different ways that you can prove someone wrong now. Remember, we can do a confidence interval, right? So we do our confidence interval, and what you say is true is not in there, we proved you wrong. So that's one way. The second way is to do a full hypothesis test and compare that p-value against the alpha level. That's what we're doing here. This is the best way. Okay, it's the most informative way. But there's actually a third way your book talks about here. I want to introduce something called the rejection region. Let's go back to our normal curve of all these X bars if 22 is in fact the real mean. If we set up an alpha level of 5%, over here, this is 5%. That means any X bar that I get in that makes it all the way into this. Now our X bar was like 22.8, which gave us 0 p-value, so our X bar was all the way over here. But any X bar in here that gives us a p-value that's less than that 5%, we're going to reject the null hypothesis, right? This has a fancy name. This is called the rejection region. Any sample mean that I get that makes it into that, I'm rejecting that null hypothesis. Well, we could figure out whether we're going to reject or not just by looking at our z-score as well. From your tables, what is the z-score? Some of you may know it off the top of your head already. What is the z-score that has 5% in one of the tails? What z-score would that be? Look it up in your tables if you need to. But what z-score would have 5% in the tail? Which one? Go look at it if you need to. 9.6. Look it up! You don't know, look it up! Starting to hear a little bit. Nice. Which z-score has 5% in the tail? A couple of ways you could be looking this up. You could look up 5%, right? It's going to be the negative one. Or you could look up 95%, right? What'd you get? It ain't 1.28. What are you looking up?
Wouldn't it be 5 on 1?
What are you looking up? What were you looking up? You were looking up 90, weren't you?
Yeah.
Yeah, think about this now. If I've got 5% here, what percent is over here? Remember, this is what our table shows us, right?
Yeah.
So would this be 0.95?
Yeah.
Okay. So what is finally 1.645, right? Isn't that the z-score that has 5% in the tail? So another way that you would know whether you're rejecting or not, you could just look at that. Didn't we get a z-score of 4.24? Isn't that past that critical X bar? You know it'd be rejecting too. So even just looking at the z-score, you knew you were in that rejection region. Okay, so that's just another way where you know. And if it was on the other side, if it was a negative value that was past it, then you know that you'd be rejecting as well. Yeah.
So you can tell whether it's good or not just by the z-score.
You could look at the z-score and know, yeah. But we want to take it to the p-value, but your book just points out here, hey, you could figure it out from the z-score. You could figure it out by looking at your confidence interval. If 22 ain't in the confidence interval, you know you'd be rejecting them. Okay? Any other questions, comments?